Hello guys, today's video is a different format. It's also a very different topic, and that's because I wanted to bring in some new content to my channel and start uploading videos on me solving problems for each of my class that I'm taking this semester. And this video is a little motivation for the homework problems related to electrodynamics class, and we are following Griffith's textbook very closely. And I thought before I just start randomly posting any problems, I was gonna do a little intro to motivate everything that I will be doing in the next videos. And the thing is, when I was preparing for the midterm, I found myself really confused by some of these questions, or like all of these questions and a few others. And I could never figure out why do we have so many different methods for calculating potential and when to use each method, and why do you need that? Why do we need to know the potential? How is it useful in real life? And the thing is, I took some time to go through the textbook, through the sections, through the chapters 2 and 3, and try to understand the bigger picture, how all these methods fit in within the bigger picture. And that way I was hoping to kind of make like a map, concept map of different concepts and how they relate to each other. And I think I was somewhat successful, and I wanted to share this with this video. So to start off, to answer these questions, I think it's important to figure out first, why do we even need to know the potential? And when you start studying electrodynamics, we usually start with electrostatics, and we are taught to find the electric field. First, we needed to find an electric field of a single charge, and then electric field of a few point charges, and then we build up to the electric field due to the distribution, continuous distribution of charges. It turns out that the integral solving for electric field is quite difficult to solve oftentimes, unless we have a really nice symmetry where we can use Gauss's law, and where this integral looks like this. Okay, so this looks quite simple, but once you get different charge distributions, try to describe the geometry of the problem, sometimes these integrals become really difficult to solve, especially that we have a square of the distance in the denominator. And the much easier way to solve for the electric field is to first find the potential, which is initially defined as this. Which is oftentimes easier to solve than this one. And then once we find the potential, the electric field can be found by using this relationship, which is, so the gradient of the scalar function v. So taking the gradient is a straightforward thing, even if you have spherical coordinates or cylindrical, well, and Cartesian. Anyways, yeah, Cartesian case is the simplest out of the three. In the subsequent sections, like after we learn how to use this thing, we move on to trying to find the potential, so we can calculate the electric field like this. And so all the methods that follow usually concern with finding the potential first, without having to worry about knowing electric field and just relying on other quantities which we can physically control, like charge and charge densities. So it could be rho, lambda, sigma. For the, like, rho is the volume charge density, lambda is the line charge density, and sigma is the surface charge density. And how useful is knowing the electric field? Well, we do need to know electric field to be able to predict how electric charges respond to electric forces. Let's say we have some proteins and we want to know how electric field affects them, and so forth. Like, there are many applications in real life where we do really need to know what the potential, what the electric field is and how we can change it. if it needs to be. And so there are various methods for calculating that potential. If you look at this example here, and this expression pertains to the static charge distributions, which means their charges are not moving. They might be uniform charge distributions or non-uniform, but the charges themselves are not free to move. Then there is also another definition of the potential, which is dependent on the electric field. And this relation is nice, but then it's kind of useless in some sense if we don't know what the E is. And we are actually after the E, like that's what we want to find in the first place. And that's what this equation is going to help us to do. It's kind of the reciprocal of this one. And so there are different methods for finding the potential. If we know things like these quantities, which are independent from electric field. Especially if we consider the situations where we have charge distributions that are non-stationary or like that are non-static. Let's say we have a conductor and we put some charge in it, and then in the conductor the charges are free to move once they see some, quote-unquote, see some charge close by. They will be moving within the conductor, and in that case it's a lot harder to use this expression compared to the other methods that were developed after that. And in this situation where we have the charges that are within the conductors and that could move freely within the conductors, since there is a change in one variable that's causing a change in another, it's a perfect candidate for using a differential equation. And the two main differential equations that describe that relationship are the Poisson's equation, which looks like this, or Laplace's equation. What we do when we study electrostatics is we solve these equations, we find such functions, such scalar functions that solve one of these equations depending on the situation. So to summarize, we have something like stationary or electrostatic, like static charge distributions, where we can determine the potential from these equations and also by using Gauss's law. But there are many other situations where this will become very difficult to solve. And then we develop a few methods to solve one of these equations. And basically what this, as I understand it, what these two mean is that we try to find a function that will describe the potential when there is, like in some region of space, like in some region of interest where we want to find the potential due to some charges outside of that region. And if there are no charges present outside of the region of interest, and we still want to find the potential like in our certain place, we use the Laplace's equation with the right-hand side being 0 because we have no outside charges that could influence the potential inside. Now, moving on to briefly describe a few methods to find the potential that will solve these equations. These are method of images, separation of variables, and multipole expansion. How do we know when to use which of the three methods? In general, the configuration of the problem determines when to use which method. The first one is method of images. And this is a mathematical tool for solving differential equations. There are very few configurations that fit to this method. Like, there are not too many. And basically it boils down to having a conductor of some sort and a point charge or some charges in some region around that conductor. There are usually two distinct regions of space, inside and outside of the conductor, or left and right of the conducting plane, or in the electric region 1 and the electric region 2. And since we have conductor, and since we have also these charges next to the conductor, or some distance from the conductor, that charge or some charges will influence the moving charges within the conductor. And so that movement will also change the potential in the region of interest. And that's when the method of images comes really handy. And we kind of make a construct where we try to make a problem more symmetric. Think of a so-called mirror charge for those point charges, and where the conducting surface acts like a mirror, basically, and we created symmetry so that the potential on the surface, either 0 or some other value, is our boundary condition. So that's method number 1. Then there's a standard method for solving differential equations, which is separation of variables. So this one helps us to solve a Laplace's equation directly, and it is applicable when we know either a potential or a surface charge on the boundary, and we want to find the potential inside the bounded region. And when I was doing this review, it became clear to me why in the separation of variables we always use surface charge density. It's because the boundary of some volume of space is usually a surface, and that's when we use the surface charge density. And the next method, and the last one, oh, and by the way, in the separation of variables method, it also depends on how many dimensions we have. The Laplace's equation of this form has could be one-dimensional, could be two-dimensional, or three-dimensional. And in one dimension, the solution to this is relatively straightforward. It's just the equation of the line, basically. But in 2 and 3 dimensions, this one becomes partial differential equation, which is very often solved by the separation of variables method. And so the last one is multipole expansion. So when do we use multipole expansion? If we are very far away from a localized charge distribution and we want to find the potential at a far distance where the distribution of charges looks more like a point charge because of the distance to it is so large, we can use a series representation of a potential function that is used to describe that potential. And this assumption that it looks like a point charge is what gives us the starting point to be able to do that, where we can use that expression for the potential. And then expand it in terms of the power series of 1 over r. And that expansion will allow us to very closely represent the potential function in some region of space where the distance to it is really large. And in most cases, we also use spherical coordinates. Okay guys, that is pretty much it, what I wanted to say for this introduction. You probably can tell I was a bit nervous when recording this because I've never done any videos of that kind. But really going through the textbook with the intent of trying to get the bigger picture helped me to structure my thinking a little bit. And I think I'm a little bit more prepared to handle any problems that come my way. Provided I do know how to use each method mathematically, because there is like a lot of other things around each method that I can't possibly fit in this video, and it's not the point. The point is just to give a starting point of where the following homework problems fit in, which category they fit in the best. And that's about it for this video. I will see you soon, guys. Bye.